Welcome to the third lecture on the orbital mechanics. In this lecture, we are going to see about two-body problem. So, in universe, each and every body is attracted to each other. When the distance between the body is larger, then the motion of two close bodies is influenced only by the gravitational forces alone, only by the mutual gravitational forces alone, and all other body effects are negligible. So therefore, most of the orbital mechanics can be treated as solution to two-body problem. The determination of motion of two-point masses which are subjected only by their two mutual gravitational forces by considering both bodies are homogeneous spheres are the assumptions in the two-body problem. When deviation occurs from this assumptions, then that is, the deviations like the bodies are not true point masses, they are not homogeneous spheres, and some other forces are acting on them, then such forces are usually very small compared to the gravitational force, and these effects can be treated as perturbations over the solution to two-body problem. In this session, the general two-body problem is explained first. Then the special case of motion of very small body compared to the primary central body, that is satellite motion about the earth, is described in detail. Okay, first let us consider the homogeneous spherical system in an inertial frame. The homogeneous spherical bodies are m1 and m2 as per Newton's law of gravitation. The force F21 is exerted on the body 2 by the body 1 is given by F21 is equal to gm1 into m2 divided by r square. So here I am going to introduce a negation sign in this equation because the forces between them is attractive in nature. Where because I can even say I am taking F21 as negative because my R vector is moving in this direction, but the force exerted on M2 by M1 is in the opposite direction. So because of which I am making this F21 as a negative vector. Again, the unit vector UR is nothing but R, which is nothing but R vector divided by modulus of R. Here, the R vector or the vector notation is represented by the bold font. So throughout this derivation or throughout this lecture series, we'll be using the bold font to represent the vector notation. According to the Newton's second law, for the object m2, the force is also equal to mass into acceleration, which is nothing but m2 into r2 double dot. R2 is actually the position vector of m2 with respect to the origin. Now here, in order to get the acceleration and double differentiating it in order to get the force F21, that is equal to m2 into r2 double dot. Now, by equating the equations 4 and 5, I get m2 r2 double dot is equal to, that is mass into acceleration of the second object is equal to minus gm1 m2 divided by r cube into r. Using the Newton's third law, the force exerted on body 1 by body 2 can be written as F12 is equal to minus of F21. We know that the force is like mass 1 is will attract the mass 2 by its gravitational force, and mass 2 will attract mass 1 by its own gravitational force. They are opposite to each other. So that is why F12 is equal to minus of F21. As explained earlier, we similarly for the object M2. Similarly, for what we have done for the object m2, the same can be applied to the object m1. Here, the mass into acceleration of m1 is equal to gm1 m2 r cube into r vector. Here, the negation sign is not used because we have already incorporated the negation sign in the F21. Okay. Now, when we are trying to find the center of mass of this two-body system, it is nothing but the weighted average. RC is equal to, or the vector RC is equal to m r1 plus m2 r2 divided by m1 plus m2. Here, when we want to find the acceleration of this center of mass, then RC double dot is equal to m1 r1 double dot plus m2 r2 double dot divided by m1 plus m2, which can be easily we can easily get this equation just by taking double differentiation over the equation 9. Okay, so now when we add the equation 6 and 8, when we add the equation 6 and this equation and this equation, when we add these two equations, here there is a negation, here there is no negation, automatically this two will be cancelling each other, this two will be cancelling each other. So all we have is that, so that two will be cancelling each other. All we have is that m1 into r1 double dot, that is mass 1 into acceleration of mass 1 plus mass 2 into acceleration of mass 2 is equal to 0. When I add these two, I'll have that as 0. Okay, so this shows that acceleration of center of mass is 0. Okay, now the center of mass of two body system can be considered as a inertial frame, because the mass 1 into its acceleration plus mass 2 into its acceleration, that is equal to 0. Now equation 6 and 8 can also be written in the form where here we had m1 m2, here we had m2, that is getting cancelled out with each other. So I have r2, that is acceleration of mass 2 is equal to minus gm1 r cube by r. Similarly, for mass 1, we can write acceleration of mass 1 is equal to gm2 divided by r cube plus r. So when I subtract the equation 13 and like when I add the equation 13 and 12, I'll have like r2 into r1. So like when I subtract these two, 13 from the equation 12, then I have r2 minus r1 is equal to r2 minus r1 is equal to g m1 plus m2 divided by r cube into r. So I'm subtracting 13 from 12. I have this expression. Then by the definition of position vectors, I have so this is r1, this is r2. This vector r is nothing but r1 minus, sorry, r2. This is r1, this is r2. So r2 minus r1. So r double dot, the acceleration of this position vector is nothing but acceleration of this position vector is nothing but r2 double dot minus r1 double dot. So now using the equation 16 and 14, it can be written as using the equation 16 and 14, I can replace this by r. So I'm getting r double dot is equal to g m1 plus m2 divided by r cube into r. Now this is the acceleration of the position vector between r1 and r2. Now what we actually want to do is to find the acceleration of mass. Let us, if we consider m1 as the primary and m2 is the secondary object, then we are supposed to find the equation of motion or the acceleration of mass m2. That is what we are aiming at. So we are first finally deriving at an equation where we are just finding the acceleration of the position vector. So what is the acceleration of position vector, which can be finally written as r double dot is equal to minus mu divided by r cube into r, where mu is nothing but the gravitational constant, that is equal to g into m1 plus m2. It is a constant for a specified two body system because g is constant and m1 plus m2 is constant. Mass is not going to change. Okay, since the center of mass has zero acceleration, it can be considered as an inertial reference, and motion of the each body can be defined about the center of mass. We can find the motion of the body about the center of mass. Okay, so motion of the body about the center of mass. See, r2 and r1 are the position vectors with respect to origin. Now what we are going to do? We are going to find the same motion of the object with respect to center of mass. Okay, so we are going to use the position vectors with respect to like center of mass. Under that condition, r is equal to r2 minus r1. So since the position vectors of the center of mass, so the position vector of center of mass relative to itself is 0. We know the position vector of the center of mass relative to itself is 0. Based on that condition, m1 r1 plus m2 r2 is equal to 0. So the position vector of r with respect to r is again 0. So that is m1 r1 plus m2 r2 is equal to 0. So from this expression we get r1 is equal to minus m2 m1 divided by m1 into r2. Okay, what I'm doing now, I'm using the equation 21 in the equation 19. So I'm getting r is equal to m1 plus m2 divided by m1. So I am going to use this r. I am going to use this r. So equation of motion of m2 here, m2 is nothing but m2 into r2. So remember, this r2 is with respect to the barycenter, not with respect to the origin. Okay, so this acceleration r2 double dot is equal to minus g m1 into m2 divided by r cube into r. So we know this is nothing but the position vector between r1 and r2. So when I want to find, I want to find acceleration of the second object with respect to the barycenter. In order to get that, I am substituting the value of r I have found here in terms of r2, so that I can get the expression only in terms of r2. So when I do that, I'm getting the expression that acceleration or I'm getting only the acceleration of mass m2 with respect to, in terms of the distance r2 alone. So that is nothing but g into m1 cube divided by m1 plus m2 whole square into r square r2 divided by r2 the whole cube. Okay, again this r2 is a vector. Here one r2 in the r2 cube, like r2, which is a vector, divided by r2 is nothing but unit vector along r2. So the equation is unchanged. Okay, so see what I am doing, I am substituting r is equal to m1 plus m2 divided by m1 into r2 in this expression. So I am substituting here and also here. Okay, so I am replacing r and r cube. So I'll get r is equal to m1 plus m2 divided by m1 into r2 the whole cube in the denominator, and r is equal to m1 plus m2 divided by m1 into r in the r2 into the numerator. Okay, the final expression is this. Okay, this expression 24 gives the motion of m2 about the center of mass. The path of m2 related to the center of mass is a conic. Conic is nothing but a cross section of a cone. When you cut the cross section of the cone, either we can get a circle or an ellipse or a parabola or a hyperbola. You can get any of this. So if you want to get ellipse, then this condition has to be satisfied, and this condition has to be satisfied for the parabola, and last one for the hyperbola. Okay, so we'll see that in detail now. So we have, what we have done is that we have just found the motion of r2 with respect to, or the motion of r2 is determined with respect to motion of r with respect to the center of mass of the object. Okay, now so far whatever we have considered is under the consideration that the both masses of a considerable size. Now we are going to the special case. Let us consider the sun and earth system. The distance between the sun and earth is almost 150 million kilometers, whereas the center of mass of the system is in the order of 455 kilometer. Okay, so the angular velocity. So now you can have the approximation that it is almost you can have the approximation that the center of mass is almost on the center of mass of sun. Okay, now the angular velocity of the line joining the sun and earth is nothing but is omega, and it is given by omega is equal to v1. V1 is nothing but velocity of the sun divided by r1. R1 is nothing but the position vector with respect to the barycenter for the sun. Okay, that is equal to v2. V2 is nothing but the velocity of the earth divided by r2. R2 is nothing but r2 is nothing but distance of the center of the earth with respect to center of mass of the system. Okay, so now let me make it clear. It is mentioned that it is the angular velocity of the line joining the sun and the earth. When we consider this two body system, if you consider m1 as sun and m2 as the earth, it is nothing but angular velocity of line joining the sun and earth, which is nothing but this one. See, this line, the position m1 m2 line is actually rotating. So this is rotating. Both are rotating. So the angular velocity of this line, right? This line is nothing but omega, and it is a ratio of v1 r1 that is equal to, that is a constant, okay? That is equal to v2 by r2. Okay, now therefore the velocity v2 of the earth m2 about the center of mass is in the order of 30,000 million second meters per 30,000 meter per second, whereas of the sun is on the order of 0.1 meter per second. It is, which seems to be like almost stable. So when you see these two systems where the sun size is very large and the motion of the earth, like when the size of the earth is very small compared to the sun, we can see that the acceleration of the velocity of the sun is just 0.1 meter per second, which means it seems to be almost stable, not moving, because the center of mass is almost coinciding with the center of mass of the sun, which means the movement is not even visible. We can consider it to be almost, it is not visible, so it appears to be stationary. But when you see the velocity of the earth, it is moving with the velocity of 30,000 meters per second, which means it is revolving at the velocity of 30,000 meters per second. So it seems that the mass m2 is moving with a higher velocity around the mass m1. When m1 is far greater than m2 in the case of Earth satellite system, the center of principal attracting body is taken at the center of mass. Hence, it is considered as the origin of the inertial system. Therefore, the governing equations of a two-body system is given by, which we have already taken. So, r double dot is equal to minus gm1 divided by r cube into r. Here, where g1 m1 can be replaced by mu. I'm ignoring the mass m2 because it is of very small size compared to m1. Now, where m1 is the mass of the larger body and a gravitational constant mu is g into m1. The value of earth gravitational constant is nothing but this value, 3.986013 into 10 to the power of 5 kilometer cube divided by second square. So, okay. The equation 27 describes the motion of restricted two-body system, because one body we have an assumption, so it is called as restricted two-body system. Now what we are doing is that we are taking a cross product, okay, cross product of equation 27. We are taking a cross product with respect to equation 27. So cross product of r into r double dot can be written as d by dt of r cross r dot. So that is equal to, when I distribute this system, I can write this as r dot cross r dot plus, so I am taking this differentiation inside, I can get r dot plus r dot plus r into r cross r double dot. Okay, this eventually leads to 0 using the equation 28. Using the equation 28 in the equation 29 makes it 0. Okay, makes it 0. We know that r cross r double dot is 0 because the rotation or the acceleration of center of mass is 0. So because that is what this is. This is 0 because the acceleration of center of mass is 0, because the system is an inertial system. That makes this as 0. Similarly, the cross product of the same vector is going to be 0. So this leads to the equation dou by dou t of r into r dot is equal to 0. Now we are going for now we are considering the angular momentum of the mass h. So which is nothing but h. H is nothing but position vector into linear momentum. Okay, position vector into linear momentum, which is nothing but a constant. So h is nothing but r cross r dot. So where r and r dot are normal to h and the orbital motion of mass m2 is in the plane normal to h. Okay, let A be the area swept by the line joining the two bodies. It is not now. We here the line joining the two bodies m1 and m2 is some r. Now, when you consider the object m1 is almost stationary, now the area swept by this r. So I think you remember the Newton's second law now. So if this is a orbit, this is the area swept. So this is the area swept by the object in some other time. So the area here, what I'm doing is that the area swept by the line joining the two bodies at specified time is given by dA by dt is equal to half r into r dot. This we have seen, which is nothing but half r into r dot. Where that expression we have seen, this can be written as half h, which is a constant. So this proves the Kepler's second law, which we have already proved in the previous expression. There itself we have proved. Okay, then now, the solution to the expression 27, this expression can be bought by taking a cross product with h. So, when you take the cross product with h, you'll get one thing. Again, with the same expression, for the same expression, we'll get the dot product to get the energy. So, we'll first derive the motion, position, and then we'll position and then we'll derive for the energy of the same body m2. Okay, so first we are taking cross product of equation 27 with respect to h. Okay, where h is nothing but the angular momentum, and angular momentum is constant according to the law of conservation of momentum. Okay, h cross r double dot is equal to minus mu divided by r cube into h cross r. These are just the mathematical manipulations. So which can be again written as d by dt of h cross r dot, that is equal to, when I expand this again, d by dt of h cross r dot can be written as h dot cross r dot plus h dot cross r double dot. So we know h is constant, so obviously h dot is becoming 0. So h dot cross, so the equation can be reduced to h cross r double dot is equal to d by dt of h cross r dot. So the right hand side of the equation 33, which is this right hand side of the equation 33, can be can be written as the right hand side of this equation can be written as 1 by 3 h cross r. So 1 by 3 h cross r, 1 by 1 by r cube h cross r, that is equal to 1 by r cube. H can be replaced by r into r cross r dot. So this is triple product which can be expanded as r into r dot minus r dot into r. Okay, now using the equation 37 and equation 36, we can write this 1 by r cube h cross r is equal to r dot. So 1 r can be cancelled, minus r dot r divided by r square. Okay, divided by r square. So this is nothing but dou by dou t of r by r, dou by dou t of r by r. This is, we know that dou by dou t of r by r, this is differentiation of, this is nothing but differentiation of UV method differentiation, right? Which is similar to UV method differentiation. So we are replacing it by this. Okay, so when I substitute this in the expression 33, when I substitute that in the expression 33, whatever we have got, so finally we have dou by dou t of h cross r dot is equal to minus mu dou by dou t by r. So what I'm doing, I have taken the left hand side and I made this. I have taken the right hand side and arrived at this point. I have made this is equal to this. So I am substituting both in the expression 33. So I am getting dou by dou t of h cross r dot is equal to minus mu dou by dou t of r vector divided by r. Okay, by integrating the above equation, we get h cross r dot is equal to minus mu r by r plus e. This e is very important. This e is nothing but a dimensionless vector of integration, and it is called as eccentricity. It is a vector again. It is nothing but the eccentricity. Okay. And this is what we have arrived at. Then we are going for the next thing. Okay. So this expression is rewritten in this form. Okay, now we are taking the dot product of this 42, expression 42 with h. we are taking dot product with respect to angular momentum. We know H is perpendicular, though H is perpendicular to R and R dot, which means R dot H is nothing but 0. Dot product of two parallel vectors is 0. Similarly, the vector r dot cross h is perpendicular to the both r dot and h. Therefore, we know means the vector r cross h, the solution will be in the plane perpendicular to both r dot and h. So because of which this dot product is going to be 0 again. That is going to be 0 again. So this is going to be 0, which considering this expression, considering these two in this above expression, we have E dot H is equal to 0, which means E is perpendicular to H and therefore lies in the orbital plane formed by R and R dot. E is a vector along the line of apsides. E is the vector along the line of apsides. Okay, so now to express the scalar equation of motion of two body, we take the dot product of equation 42 with R. We have taken the dot product with H. We have taken the dot product with H before, and then we prove that E is perpendicular to H. Now again we are going to take the dot product with respect to R for the same expression, the 42. So under that condition, R into R divided by R plus R into E. So dot product is usually the projections, okay, that is equal to R dot cross H divided by mu. Using the vector identity, we can interchange the dot product and cross product here, so that we'll get it as R cross R dot R cross R dot into H is divided by mu. So R into R is nothing but R square, R cross R dot is perpendicular, which is nothing but H. H dot H is nothing but H square. So this expression can be written as R plus R dot E is equal to H square by mu. So the dot product of R and E can be written as RE cos theta, RE cos theta. So where E is the magnitude of eccentricity vector, E is nothing but the magnitude of eccentricity vector, theta is the angle between eccentricity vector and the line of the eccentricity vector, that is line of apsides, and R. So what is line of apsides? Line of apsides is nothing but if you have a two body system M1 and M2, okay, we have this. So M1 and M2. Consider an orbit, consider an elliptical orbit. Here is the mass M1 and M2 is rotating around it. So the farther point is nothing but the apogee point, the nearer point is nothing but the perigee point. So the line crossing the line joining the apogee point and the perigee point through the center of mass is called as the line of apsides, and that is the line of apsides. So theta is the angle between the eccentricity vector and that is line of apsides, and R, it is angle between this and the vector R, and it is given by the expression. Then the equation 47, this can be rewritten as this. Okay. So in general, the conic section, that is the cross section of the cone, conic section locus of all points follows the constant ratio. Constant ratio means the ratio of RC, the ratio of RC and DC is constant. So RC and DC, RC by DC is constant. PC by D naught is again a constant. It is of same value, okay, is constant, which can be shown on the figure 3. Okay, RC is the distance point from the focus. RC is the distance of a point from the focus, whereas DC is the distance of the same point from the directrix, okay, from the directrix. EC is nothing but the eccentricity of a conic section. EC is nothing but the eccentricity of a conic section. Though this eccentricity can be written as is nothing but the ratio, is the constant ratio, that is RC by DC is equal to EC. Okay, so when I substitute all this here in the equation 50 and 51, using the equation 50 and 51, we know that RC is equal to PC divided by 1 plus EC cos theta C. Okay, it is all with respect to the center of mass. Now, if this eccentricity is 0, then it is a circle. See, a proper cross section of a conic. This is a circle. If the eccentricity is between 0 to 1, then the path will be of ellipse. If it is equal to 0, it's a parabola. If it is if it is equal to 1, it's a parabola. If it is greater than 1, then it is a conic. It is a hyperbola. It is a hyperbola. We have seen the same thing with respect to the velocity of v2 with the gravitational constant. Okay. Therefore, the trajectory of a smaller body with respect to the bigger body in the gravitational field is represented by the equation 49, which is represented by the equation, equation 49. Is a conic section which is given below. It is a conic section which can be either a circle or an ellipse, parabola, hyperbola, but we know that so ellipse and circle form the closed loop system. Okay, where semilattice rectum of the trajectory is nothing but p is equal to h square by mu. So here we can see the orbits in this graph. We can see in this diagram we can see that the typical orbits or trajectories of various orbit with eccentricities, but it has the same focus and the same periapsis, which means perigee point and the focus are remain same, but when the eccentricity alone varies, how the orbit is changing is explained in this diagram. Now, the cross product with the equation, we have taken the dot product of equation 22. Now, we are making a cross product for equation 22, this equation 22 with respect to R in order to, so we are making in order to find the energy. In order to find the energy. Okay, so we have find the motion, like how the motion of the second object is going was with respect to the barycenter. Now we'll take the same expression, and now what we are doing, taking the same expression, the cross product of equation 27 with a specific relative angular momentum per unit mass is nothing but angular momentum per unit mass. We are taking the cross product, and that gives the motion of a smaller body in the central force field. So the dot product and the equation 27, so we have taken the cross product and it has given the equation of motion for this. Now the dot product of equation 27 with the linear momentum has given the energy at point. So when the dot product of equation 27 with linear momentum will give the energy at any point on the orbit, which is explained below. Linear momentum is nothing but mass into velocity. So when I am therefore the specific linear momentum in the sense per unit mass, so it is nothing but r dot. Taking the dot product of equation 27 with respect to r dot, I have r double dot into r dot is equal to minus mu r dot r into r dot divided by r cube. Again, this can be rewritten as half, because why I have mentioned it is half, because if you see it is, we have written it as half because when I take this dou by dou t, I have two expressions. Okay, I have two expressions. One is nothing but, so that if I write like this, so this will become dou by dou t of r. So this can be written as r double dot into r plus r dot into r double dot. So this is 2 times r double dot into r. So if I want to write it in terms of this, I have to make half d by dt into r dot, that is equal to r double dot r dot. Okay, now I am assuming v is equal to r dot, which is nothing but the velocity of the position vector. So when I make it as v, I'll have half d by dt of v square, The right hand side, first we have taken the left hand side of the equation and we are writing it in this form. Now we are taking the right hand side of this equation and we are trying to manipulate it the same way, like mu dou r into r dot by r cube, which is nothing but r dot by r square. So that is equal to minus dou by dou t of mu into r. this is nothing but dou by dou t of 1 by r is equal to r dot by r square. So you'll get this. So in order to make that, we are just using the manipulations. Okay, so this is looking like a differentiation of this, right? So we are writing in the differential form. We are writing this in the differential form. So now we have arrived here with this, and we have arrived here with this. Okay, so we are substituting both whatever we have arrived at in the 59 and 60 in the expression 56. So we get dou by dou t of v square by 2 minus mu by r is equal to 0. So when I integrated, we have v square by 2 is equal to mu by r into epsilon, where epsilon is a constant, that is nothing but the total energy. V square by 2, we know half mv square, because we have taken it as per unit mass, so mass is not here, but if not, this is representing the kinetic energy. This represents the kinetic energy per unit mass, where mu by r is nothing but the specific potential energy, that is due to the gravitational field. So it is the specific potential energy of body m2 in the gravity m1. So equation 62 gives the total mechanical energy per unit mass. So it gives the total mechanical energy per unit mass, which we will again use when we are finding the escape velocity. So here it is a total mechanical energy per unit mass. Also, equation 62 gives the conservation of specific mechanical energy for a defined trajectory. Okay, the total energy at any point of the trajectory is given by equation 62, and equation is also called as vis viva, that is living force equation, is also called as living force equation. So what we have done, we have taken the expression r double dot, the basic expression for the basic expression for the acceleration of the position vector, and we have taken the dot product with respect to h, angular momentum, and we have arrived at the motion of object, where we have arrived at the motion of smaller body in the central force field. Again, we have taken the dot product of linear momentum, and we have arrived at the energy at any point. So we have find the motion at any point for that body, and we have arrived at energy again. We have find the energy at any point for the second body under the revolving around the first body under the influence of the gravitational force of this bodies. Okay, the equation r double dot is equal to mu by r cube into r is the equation governing the equation governing the two body system. This is the equation that is governing the two body system. We are taking this, and we are taking the dot first cross product with the angular momentum, then we have taken the dot product with the linear momentum in order to find the position and the mass. In order to find the position and the energy of the secondary body m2 with respect to m1, or with respect to the barycenter. So this is what we have done in the two body problem. We have taken the two body problem. We have arrived at the expression holding the expression which is actually representing the two body system. And then from that expression, by taking the cross product with h, and that is angular momentum, we have arrived at the equation that is stating the motion of m2 around m1 or m2 around the barycenter, and then we have taken the dot product with respect to the linear momentum, and finally we have arrived at the energy equation. So the energy equation, the total energy of the system or energy of the mass m2 at any point in the orbit is determined in the second equation. So hope you are clear with it. If you have any doubt, feel free to mail me at professordeepti@gmail.com. Thank you.